A wide range of mechanical designs and engineering applications make use of hyperelastic materials such as rubbers. For example, rubber gaskets and O-rings often act as seals between two components in a mechanical assembly. In many of these applications, the components made of hyperelastic materials undergo large strains. Modeling such cases can be challenging since the elements can undergo excessive deformation, which may stop the progress of the simulation. In this video, we will discuss why element distortion errors occur and provide some solutions to overcome them. So let's get started. Hyperelastic materials are those that can undergo a large amount of deformation without incurring damage or plastic deformation. A very common example in our day-to-day lives is a rubber band which responds elastically even to large strains. The stress-strain relationship in case of hyperelastic materials is generally not linear, and various material models are available to capture the response. For example, Neo-Hookean models, Mooney-Rivlin models, Ogden models, etc. Since hyperelastic materials can deform to fill up gaps between two mechanical components, they are often used to manufacture O-rings and gaskets for sealing purposes. In a number of applications, the hyperelastic materials undergo large deformation and are also in contact with mating parts. Due to this reason, modeling them can be quite challenging since such simulations have geometric, material, and contact nonlinearities. One of the frequently encountered errors when using hyperelastic materials is the excessive element distortion error. Due to the highly nonlinear nature of the simulations, certain local regions of the model may undergo excessive deformation. This in turn may lead to a non-physical shape of certain elements in the mesh. For example, consider the element shown here. Ideally, in case of a hexahedron element, the edges should have an aspect ratio as close to 1 as possible, and the angles between its edges should be close to 90 degrees. The reason for this is that in finite element analysis, in order to facilitate numerical integration, the nodal coordinates in the physical space are mapped to a cube in the natural coordinate space. Having an aspect ratio of 1 and angles close to 90 degrees makes this mapping very easy. Now, if the body was made of a hyperelastic material, the body may deform excessively at a global or local level, causing some elements to deform so much that this mapping of nodal coordinates from physical space to the natural coordinates becomes less and less accurate until it is no longer possible. This inaccuracy generates an excessive distortion error, which prevents the solver from proceeding further. So how do we overcome these element distortion errors? Element distortion may occur due to a number of reasons, and the possible fixes for this type of error can be broadly classified into two categories. First, controlling the quality of mesh, and second, checking the model setup. The first category consists of several options such as using elements less susceptible to distortion, using appropriately shaped elements, or even applying loads in smaller increments. In certain extreme cases, we may also need to use nonlinear mesh adaptivity, which is an advanced technique of improving the mesh quality by remeshing. The second category of fixes includes checking the overall model setup, which includes ensuring that the material definition is valid for the case at hand and that the material model is stable. If the model at hand has contacts defined, then we need to ensure that all possible contacting surfaces are accounted for. We may also need to tweak certain contact settings or modify the design to help redistribute the localized high stresses and strains. This might seem like a lot of things to remember, but don't worry. We will now simulate a slab of rubber being compressed by a rigid block in Ansys Mechanical. We will learn to understand the error messages and use them to diagnose and fix the underlying issues. We are inside of Ansys Mechanical and we have two bodies, a rubber block and a rigid block. The material we are using for the rubber block is neoprene rubber that we have fit with a 9-parameter Mooney-Rivlin model. We have defined a frictional contact between the bodies. Notice that we have included the sides of the blocks in the contact definition, as we expect the rubber to deform significantly and may in fact contact on the sides. For the contact settings, we have specified a friction coefficient of 0.2 and the remaining contact settings are left as their default values. For the boundary conditions, we are pushing down on the rigid block with a specified displacement, while the bottom of the rubber block is fixed. For the mesh settings, the element order is set to program controlled, and this will result in quadratic elements with mid-sided nodes. For the analysis settings, we leave the automatic time stepping to program controlled. Large deflection is turned on as required for hyperelastic material models, since we are looking at large deformations and large strains. We also turn on a diagnostic feature that allows us to see the Newton-Raphson residuals, so we can visualize locations of the model with high residual forces causing non-convergence. To do this, we set Newton-Raphson residuals to 4. Before we run the model, we wish to turn on a diagnostic feature which will identify any elements that are experiencing excessive distortion. So in solution information, we set the identify element violations to 4. Okay, let's run the model. We can see from the status that the solution did not complete. Let's have a look at the solution information solver output to see the messages. The latest messages indicate that some elements have become highly distorted. To see where in the model the element is located, we can now find an object the solution information has been created that we can click on to highlight the element in the mesh. We can see the element lies at the location of the edge of the rigid block, and this is the region we expect to find localized deformation and higher strains. Recall that by setting the identify element violations to 4, we have this additional useful information. Let's also now look at our deformation. We insert a total deformation to look at the deformed mesh. Now evaluate the results. Here we are seeing the unconverged results, and notice the elements are becoming distorted from their original cube shape. This is most evident where we saw the highlighted element from the identify element violations. In fact, if we look at the last converged substep, we can see the deformed shape and how we are seeing more localized deformations where the edges of the rigid block touch the rubber block as expected. Let's also insert an equivalent strain for our last converged substep just to get an idea of how much straining is taking place. We can see we are at less than 50% strain. Now let's implement a few changes to try and proceed further with our solution and overcome these issues. Going back to the solution information, there is a warning about our hyperelastic material model that it may become unstable. While this may not have been the reason for our element distortion for the amount of simulation we have solved so far, but it may come into play later, so it is best to address it now. Go to Workbench Engineering Data for the system. Picking our material and the hyperelastic material model, we see we have a 9-parameter Mooney-Rivlin model specified. The higher order model is creating an instability in the curve fitting of the hyperelastic material model to our biaxial test data. So let's switch to the second order Ogden model and solve for the curve fit using the absolute error. Now we can see there is no instability in the response and the fit is quite good. Let's copy the computed values to the material property to use them in our simulation. While we won't get into the details of curve fitting in this video, but instead focus on the element distortion, it is worth noting that for the curve fit, it is best to have a full set of data, which we do have with our 3 sets of test data: uniaxial, biaxial and shear. This permits the hyperelastic material model to be used for the different modes of deformation, tension, compression and shear. Providing fewer than a full set of test data may not enable us to predict the general response to another deformation mode accurately. Finally, our data should go far enough to cover the range of strains we expect in our simulation. So recall that for our incomplete solution, our strain already has gone out to less than 40% and our test data goes out to 2 or 200%. Following the completion of a solve, it is important to check that the strains are still within the bounds of our material data. Now refresh and edit to return back to mechanical. Next, let's make changes to the mesh settings. It's a good idea for us to change our physics preference to nonlinear mechanical. This changes some of the mesh settings in attempts to have a mesh that will be less susceptible to mesh distortion. Next, we change the element order from program control to linear. Recall that program control resulted in quadratic elements. Linear elements are a better choice in this case as they can experience more distortion before becoming so highly distorted that they can no longer be mathematically valid for the solution. Now generate the mesh. Looking back at our error message, it indicated incrementing the load more slowly as a possible solution. So now let's make some changes to that effect in the analysis settings. The auto time stepping was left at program control, and while this is generally a good starting point, for non-linear models we will typically want automatic time stepping turned on so that the solver can adapt the time step and hence the incremental load that is applied. We will set the initial to 20, minimum to 10 and maximum to a fairly large number like 500. Okay, let's run the model. This time the model solves to completion and we do not have any excessive element distortion errors. Let's animate the total deformation plot to get a sense for the material behavior. Let's also animate the equivalent stream. If we pause at the final substep, we can see our peak strain and the value is just over 100%. Recall that our test data went out to 200% strain, so we are safely within our available test data range that our model has been fitted to. Finally, drag and drop the remote displacement onto the solution and evaluate the results. The chart shows the nonlinear trend of the force required to squeeze the rubber. If we wish to compress the rubber block even further, then we may need a few more modifications. The rigid block we used in our example has sharp edges, due to which very large local deformation may occur on the rubber block in the regions where these sharp edges contacted. This in turn might lead to excessive element distortion errors. One way to overcome this issue is to modify the design and hence the geometry of the rigid block to smoothen these sharp edges. Now, because we have redistributed some of the sharp localized strains, we can see that the rubber block can be further compressed. Another possible option is to use nonlinear mesh adaptivity or NLAD. NLAD is an advanced technique in which portions of the model are remeshed automatically during the solution, and this can be based on a mesh quality criterion which helps in avoiding the excessive element distortion errors. This is another option which can help the simulation proceed further, but discussing it is beyond the scope of this video. Finally, we can also use our judgment about the final deformed shape of a body and bias the element aspect ratios such that at final deformation, they are closer to 1. While this won't help in all cases of deformations, materials that are being uniformly stretched or compressed can benefit from changing the original aspect ratio to prevent excessive aspect ratios once deformed. For example, consider this rubber block being pressed by a plate. Since we expect the rubber to get compressed in the y direction and stretch out in the x direction due to Poisson effect, the elements will contract in y direction and elongate in the x direction. So we can generate an initial mesh such that the element edge length in the y direction is larger than the element edge length in the x direction. So now when the body gets deformed, the elements will have an aspect ratio close to 1 and thus avoid getting distorted excessively. So now let's summarize the important points we learned. First, we learned that excessive element distortion error can be common in models with hyperelastic materials, and it is inherent to many mechanical designs that use these materials. We can diagnose this error in Ansys Mechanical with the help of error messages and by using options to highlight excessively distorted elements. In order to overcome this error, we need to ensure two things. One, that the mesh quality is good, which may include using elements less susceptible to distortion, using a mesh with appropriately shaped elements, or applying the loads in smaller increments. Secondly, we need to ensure that the model is set up correctly, which includes ensuring that we have complete test data and are using a stable material model. In some cases, changes to the design geometry may be necessary to limit localized excessive element distortion. Nonlinear mesh adaptivity or NLAD can be a powerful tool, but the recommendations made in this video should be implemented before proceeding to NLAD. If you find this video helpful, please like, comment and subscribe. To find more information about hyperelastic materials or other topics, check our channel for more how-to videos and visit ansys.com/courses today.